Hey, welcome back. Today we're going to be talking about what is angular momentum and its conservation, and how do you solve problems with conservation of angular momentum. So this background that you're going to see up here is taken from an FRQ from 2023 for AP Physics C Mechanics. However, don't go away. Let's think about this. You can do this without any calculus here. I just want to introduce the idea of what is angular momentum and how do you do problems with this. I just think this is a very clear problem to demonstrate what we mean by angular momentum and how to approach some of those really key crucial ideas. So maybe you're an AP Physics student, or maybe you're a regular physics student and you need to know something about these topics. This lesson is for you. Now there's a big wall of text here. I'm not going to read all of it at you. If you want to pause and take a look at it, go for it. I'm just going to highlight some of the key ideas and want to point out that we do have an equation in the upper right quadrant over there. And there are basically two forms of this. This is our angular momentum, this L value right here. And you see the vector notation above it, that little arrow, that signifies that we're talking about a vector. I've done a screencast on how to calculate the direction of that vector. I'll put a link to that in the upper right about now. And notice that we've got a cross products. This is an R vector and P. So this is momentum, where we say P is equal to M times V. That's our basic definition of momentum. And the fact that it's a cross product tells us that we're looking at the R vector, which in this case is like the length of the rod, at 90 degrees to the other vector. The other vector would be the vector of momentum in a linear sense. That P vector and the R vector are at right angles to each other. So you could think about the motion of the rod at the instant it strikes the ball. It's going to be moving completely to the left in terms of the momentum of the ball. The ball is going to pick up a momentum going completely to the left, and that's at a right angle to the radius vector. So that's the most important aspect of what it means to have a cross product in this case. Over here, R, this is a distance. It's the distance between the axis of rotation and the center of mass of the object. So like this right here, this is going to be our R vector in this regard. That's what we mean by R. And then the I over here, this is most commonly called rotational inertia, but it can also be called moments of inertia. And it's the rotational analog of mass. It's like a rotational form of mass, and it has to do with how the mass is distributed, because that matters in rotating systems. And then lastly over here, this is angular speed or angular velocity. Alright, very good. So what's happening in this problem? This, by the way, is part 2 of a 2-part series of introducing these key ideas. I've done screencasts on this, and I just thought this was a very quick and easy and to the point way of explaining these concepts, is to go with this FRQ. And also because FRQs are kind of like a possible goal for most students, is if you can handle FRQs, you can handle easier problems as well. And so we have this rod that swings down and hits the sphere. The first part of the problem was a conservation of energy problem. This part of the problem, where there's a collision, is where there's an angular momentum problem. So in the last sentence it says, after the rod is released, the rod swings down and strikes the sphere head on as a result of this collision. Whenever you see the word collision in physics, I want you to think momentum. So if there's a collision, that's a tell that this is almost certainly going to be a momentum problem. Now the one thing we cannot do, this will be a conservation of angular momentum, but you cannot have angular momentum. You cannot have a conservation of momentum problem where you have angular momentum equal to linear momentum in the same equation. That doesn't work. You're either doing a conservation of angular momentum problem or a conservation of linear momentum problem, like just two billiard balls striking each other and bouncing off or something. In this case, we're talking about a rotational motion, even though at the end of the collision, we know that the ball is going to move at some velocity, some linear speed is what we're going to call it right here, V naught. We call it V naught, or the problem calls it V naught, because this will begin another section of the FRQ. We're not going to concern ourselves with that right now, but still we want to treat this as an angular momentum problem. Alright, so first things first, you want to decide if you're talking about, like, say, part 1 or part 2 in terms of the parts of the equations to deal with. So the initial part, we could say that the angular momentum initial, total angular momentum initial, is equal to the total angular momentum final. That's fundamentally what we mean by a conservation of something. There's some events, and the total amount of stuff before the events is the total amounts before the equal sign, and the total amount afterwards. They equal each other. That's what we mean by conservation of something in physics. Okay, so we have to decide if we're going to use the variant of equation 1 or variant of equation 2. So let's think about this. So for the initial part of this, it's the rod that's swinging down, right? So we already know what the I value is for the rod, and we know something about the omega. We had solved for the omega previously, the angular speed previously. So this is what we're going to use for the initial part of this. I can even label this as rod over here. And then if we look on the right hand side, so for the final angular momentum, it's going to collide with the sphere. Now the sphere, what we're going to use is the part 1 part of this. In other words, we have the radius crossed with the momentum. And again, this is our momentum vector over here. And so we have that R value is the length. So if we think about what we have I rod times omega. And this R, let's think about what this R is. In the context of this problem, what do you think this R is? Well, this R is going to be the length of the rod, right? And then this is going to be the mass of the rod times the speed that we have. Okay, we do know a couple other things, and I'm running out of room here, so I'm going to drag this down a little bit. But we do know what the inertia of the rod is. The inertia of the rod is over here, so we can further define what we're talking about. So we'll say 1/3 ml squared times omega is equal to L mv. So immediately these m's go away. Even though one is uppercase and one is lowercase, in this context they mean the same thing. This L cancels out one of these L's over here, and we do want to get this value over here. We do want to get this by itself. It's actually already by itself, and to take this any further, we would have to sub in from part A more information about omega. But basically, we've got this isolated as much as we can in the context of this problem here. This is going to be 1/3 omega L, but if we knew something from the first part, we could sub in what that omega is. However, we're going to wrap up this problem here. So I do want to say I've gone over all of the ideas for high school physics as well as most of the ideas for AP Physics CE Mechanics. If you have any questions or comments down below, please let me know. And I hope you all have a great day. Take care.